Many AutoML solutions use a simple algorithm like gradient boosting, but to be efficient in its implementation, it's done on low-level languages, C++, C, and so on. And if you want to customize it, it's difficult to do it because not everyone knows how to do it on Pyboost for industry stories. And now Anton Vakhrushev will talk about the open source library called Pyboost, which can be used as a stand for studying gradient boosting, for customization, checking different hypotheses that you can integrate into a gradient boosting to make it better. Okay, attention to the screen once again. Hello, my name is Anton. I work in the laboratory of artificial intelligence research. I will tell you about about gradient boosting for determination trees. It can help developers that investigate the properties of this algorithm. Gradient boosting for decision trees form an important part of all AutoML solution. You can see it in the middle of the diagram, and recently we shared an article in an archive, and you can read it yourself. Today, state-of-the-art GBDT implementations are close to AutoML itself. They are efficient, and modern boosting resembles AutoML itself. It's a standard fact for the industry, and some can work with the text, if you understand what I'm saying. That's why AutoML development should talk about optimization of data, matching attributes, and so on. Think, if we could improve boosting, we could improve quality of every AutoML solution.
Потому что это сложно.
Why people don't do it? Because it's complex. Imagine you have an idea you would like to test in boosting. What are the options? You can use modern state-of-the-art decisions, an ideal option, but you have details. Well, actually, you need customization tools, callback, but it doesn't happen all the time. Otherwise, you need to take a low-level code, and it's time-consuming and not possible for everyone. It's not obvious how different state-of-the-art implementation of boosting work. The global idea is clear, but there are details. So what is a state-of-the-art? You can write like a Scorion construction libraries. You can write a simple boosting and integrate your ideas, but it will work slowly. Well, then you will have to write reinventing your bicycle. And it's not good for testing hypotheses. That's why we developed our own library to test them with the help of boosting Pyboost, so boosting on Python. At first, we used it to test our own ideas, and we understood that the library is very handy. We wanted to do it more user-friendly and share it in open source. So you see the link at GitHub. What special is about this library? It's a classical gradient boosting algorithm with decision trees. We have all features like for Pyboost and other libraries. We wanted to make it fast. It's possible to use it in Python. So we used number and CuPy. as a library. QPy is a library that works with data array. It's similar in number with more data arrays. Even if you don't have any experience of working with GPU, you can replace NP with CP. And the last pleasant feature is that some results of our research works, we integrated into this library, and they are available. And we will talk about some of them.
To begin with, let us have a look at a simple case of using this library. So in the easiest way, if we want to have a working model, we can use this interface. So we can train the model calling the predict method. The only difference is that we do not have a regressing classifier classes, and the task that we solve is the loss function. And if we send MC loss, it understands that it needs to solve the task of regression, either simple or multitask. Customization is pretty easy. We can write callback classes that describe the logic of the actions before, after the iteration, before or after the training. And a dict is given to this method that shows the whole training, including the validation data sets and the model states and the parameters that the training occurs on. You can see the example of a code that describes customization with proportional importance on features on the ensemble. And this strategy should not work on every data set for sure, but if we can try, why not? Let us talk about the results of our researches. The first case that I would like to look at is the so-called OpenML benchmark. That is 39 data sets for classification problems that we used before the release of Light AutoML open source library to evaluate the quality of our AutoML, and we were pleased to show that the number of wins of our AutoML actually outpaces our competitors. And actually, there were also unpleasant things that we noticed. We saw the zones where our AutoML and other AutoML processed badly. One of these zones is the task of multi-class classification. For example, there were data sets for 300 classes where practically no one could work on. And this task might seem far away from prod, but still 200 or 300 is the approximate number of products that a bank can offer a client. And usually modeling one product can have non-sufficient data. So we can model this product together with one model through multi-level classification. What is the problem of boosting with multidimensional output? So let us have a look at what ways of work exist at all. For example, we have one-way-all approach when we have trees separating each class from the others. And the drawback is that it is long because you have to make a lot of trees. And Pyboost is a single tree strategy, and it gives one vector and it is better, but there are problems with that. Boosting can be generated in multi-dimensional output, and the function here will be sum of SPED function per each output. So we build one tree, but to find split is expensive, and as expensive as many outputs we have. And the global strategy with one tree is usually better. That's why we decided to take this strategy as the basis and get a better function for split search to make it more efficient. Let's have split search not around the full matrix of gradients, but on some approximation to this matrix. That's why we came up with three strategies. That is approximation of a gradient matrix with the best SVD. The second one is selecting important outputs based on gradient values. And the third one is just random sampling of these gradient values per each iteration with a proportional probability to new gradients. So the more output needs updating, the more chance for us to choose this output. We tested random strategies of tree building on different data sets. They were different in size, in number of features, and the outputs. They were 9 class identification in the easiest way and 300 classes in the worst case. Our expectations were so that, yes, we would be able to learn building these trees more or less fast, but the quality will be poor. And we tried to find some good trends, and two out of three strategies proved our expectations. So we learned to build the trees fast without losing the quality, and the detailed result will show us that where the output is around several hundreds, we can have a gradient matrix of an order of 5 or 10, and the quality will be close to full scoring function calculation. Another observation is that we have built curves of training to approximate different sizes, and it turned out that full scoring function models converge faster. But if we select the number of iterations correctly, sooner or later they will all lead to one quality, and the models with random sampling will give the same quality as the full ones, full split search ones. And we also implemented this on Pyboost, and they are in multi-output problems handling. And you can see an example of proxy split search for multi-output problems. And by default, the multi-output sketch is set to none, which means a pure split search. A very interesting option present here is that we can variate the strategy. We can choose one versus all and work with multiple tasks, and that is not all. And two of these strategies, single tree and one versus all, are like edge conditions. And for your task and for your data set, it is not obligatory that one of these strategies will be optimal. It might be optimal to build 5 trees per 100 classes, and the groups where a single tree per each iteration is built can be grouped separately, and there is a separate class for that, and the slide shows you an example how to use that to launch this mixed strategy. Furthermore, you can write customized example of how your targets are grouped. If you can come up with something smarter than random grouping, you can carry out this customer implementation. That is all I wanted to share with you. The library that we were talking about today is accessible through this link in GitHub, and just like other developments of our centers, let us share ideas, and I hope that we together will be able to make boosting and AutoML better. Thank you, Anton. That is really cool presentation. And you have said that it is hard to implement your own boosting, but you managed to do that. What kind of helped you? How did it so happen? Actually, the problem of working with multi-class and multi-label tasks was pretty acute in AutoML and benchmarks that we were talking about. And actually, we could have built good models for OpenML datasets with AutoML, but we just did not meet the restrictions, the temporal restrictions. We wanted to do it faster. And different boostings suffer from multi-dimensional output, each in its own way. And we wanted to come up with something that would help us. And these ideas might look pretty easy and simple, but that is not all. That is not all that we are experimenting with. We have much more complicated ideas, and we try to make our boosting more general one, I would say, that would not make assumptions on possible strategies of working with multi-dimensional output. And there was one more question. If we call library testbed for starting boostings, and the benchmark that we were talking about will also contain inside itself real tasks, how applicable do you think Pyboost is to solving real tasks? Well, it is applicable. Why not? Why do we pose it mainly as a testbed? Because we ourselves use it as a testbed, first of all. And second, as of today, we have done the CPU mark only. And I believe that prod DCPU is a pretty important story for inference, for sure, if not for training. Therefore, I believe that what has to be done afterwards is that. And another thing is that we do not have a strategy of working with multi-GPU, so dataset has to go into one GPU. And that is not bad news, because it now has less space there than in CPU memory, but still in prod there are usually data sets that will not go there. If there are hundreds of millions of strings per thousands of features, you would not be able to work with that. And these restrictions or constraints do not allow us to call this prod. And if there is GPU support that you can work with, if you do not have super huge data, then you can use it to solve your tasks. Thank you very much, Anton.